Imagine the height of the Cold War. The year is 1957 and a tiny beeping Sputnik satellite crosses the night sky. In America, fear mounts. If the Soviet Union can launch a satellite, what else can they do? Both the USA and Russia have nuclear weapons, and people live in fear of a surprise attack. In the late 1950s, early 1960s, communication systems were fragile. One bomb on a key telephone line, and America's entire defense system could go dark. And one radical idea takes root. Connect a few powerful computers of the day into a network that keeps working, even if parts were destroyed by an attack. It's a bold vision born from a desperate time. A vision that will eventually give birth to the internet. The plot twist here is that the internet, or more accurately TCP/IP, the code that makes the internet work, almost didn't survive. In the 1980s, big corporates, telecommunication giants, governments wanted to bury the internet, mainly because they wanted their own perfect systems to be in control. And it took a handful of stubborn but brilliant engineers to fight for the open and decentralized internet that we have today. This is actually a really interesting story about the code that built the internet and why it was almost lost forever. So it's 1957, and the Soviet Union shocks the world by launching its first ever artificial satellite called Sputnik 1. It was a shiny metal sphere, almost the size of a beach ball, orbiting the Earth every 98 minutes, sending out a radio signal. And for the American government at the time, hearing Sputnik's beeps was about the power. If they can put a satellite overhead, how long until they can drop nuclear warhead on us from space? Newspaper headlines screamed panic. Politicians demanded answers. The Cold War was no longer an abstract threat because technically it was right above their heads. In response, the US government sprang into action. They created ARPA, or ARPA, the Advanced Research Projects Agency. It was in early 1958 and it had one mission: prevent technological surprise. And ARPA was a moonshot machine. Small teams, big ideas, no red tape. They poured money into rocketry, space exploration, early missile defense, and yes, you got it, computing. By the early 1960s, computing was becoming quite critical when it comes to American defense. But the problem was that every computer was its own separate island. At the time, computers were massive mainframes housed in government labs or universities with names like IBM 790 or the DEC PDP-10. They couldn't be run by people like you and me. The computers processed data, ran simulations, guided missile systems. But if you wanted two computers to share information, forget it. So the US military leaders realized that their command and control systems, consisting of radar, early warning signs, any communications, those systems were incredibly fragile. This was because they were built like the phone system at the time. One wire goes to one place, one switchboard controls an entire region. And if you take out one node, the entire system could collapse. And that terrified strategists at the Pentagon. Imagine a Soviet missile knocking out a few key communication hubs. Suddenly, the US military can't coordinate some sort of response. So, ARPA and military scientists started asking, what if we built a communication system that actually didn't have a center? What if it could still survive even if parts of it were destroyed? And what if the network could just heal itself on the fly? Because at the time, computers were generally isolated in military labs or universities. If you wanted two computers to talk to each other, well, you would need some sort of dedicated line, almost like plugging in a landline phone to another landline phone. And the problem here is that if one line broke, or the central hub got destroyed, the whole system failed. That's when researchers like Paul Barron at RAND and Donald Davies from the UK came up with one revolutionary idea: packet switching. Instead of sending one big continuous stream of data, why don't we just break it up into smaller pieces? Each packet can travel separately, hopping through different routes. And if some parts are blocked, No problem. The packets can just find another way. It's like sending a message on a bunch of different postcards through different mail carriers, and you'll trust that they will arrive and get reassembled at the destination. And these were cutting-edge ideas because at the time, phone companies ran everything, and phone companies believed in something called circuit switching. You reserve a dedicated line for the entire communication, almost like a private road. The idea of breaking up the communication or the data and just tossing it into the network, hoping it can find its way to the destination, that idea just sounded like chaos to them. But for ARPA, that exactly was the point. They didn't want a fragile system. They wanted a system that could survive the nuclear war. And so, in the heart of ARPA, a world-changing idea started to take shape. What if we could connect our country's computers into a resilient network, one that could survive even if parts of it were destroyed in some nuclear attack? And ARPA took these ideas seriously. By 1969, a team at ARPA led by Bob Taylor and Larry Roberts actually built the first packet-switched network. It was called the ARPANET, and it started with 4 computers. These computers were based in UCLA, Stanford, UC Santa Barbara, and the University of Utah. Each of these computers were connected to an interface message processor, an IMP. This was a rugged mini computer that acted as a router. And on October the 29th, 1969, UCLA sent the first message to Stanford. It was the word login. The system crashed after the first 2 letters LO had been transmitted. It was a humble beginning, but a historic one. And soon, with some fixes, the ARPANET became live. By 1972, a few years later, it had 30+ nodes connected across universities, military sites, and even a satellite link to Hawaii. And in fact, in 1973, electronic mail, email made up the majority of the ARPANET communications. And ARPANET was cool, but most importantly, the ARPANET was a research network. It wasn't yet the global internet that we know of. It also used a specific protocol called NCP, Network Control Program, which allowed the computers to communicate. Now, NCP worked really well for ARPANET, but ARPANET was just one network. New networks were sprouting elsewhere in America and around the world, each speaking their own specific language. There was the packet radio network for wireless links, satellite networks for transoceanic links, and even commercial networks like Telenet. And these networks were all different. So yes, they can communicate internally, but they couldn't communicate to each other. So how could all these separate systems become one seamless whole? And now ARPA's mission grew beyond just building a network. Now they needed to network the networks, because none of them spoke the same language. It's similar to having iMessage, WhatsApp, Discord, Telegram. They all work great internally, but you can't get those apps to talk to each other. So enter Bob Kahn and Vint Cerf, the heroes of the story. These 2 men would eventually solve the problem and technically create the internet. So it was the early 70s now, and these 2 scientists, Bob Kahn and Vint Cerf, teamed up on a mission: make a universal language that all networks could understand. Bob Kahn worked at ARPA and Vint Cerf was a computer scientist at Stanford. So their question was, how do we make ARPANET talk to other networks? They weren't trying to control the networks, they just wanted to create a common set of rules. So picture the scene. You have Kahn and you have Cerf huddled together, sketching diagrams on Notepad in some cramped Stanford office. And the challenge was to design a procedure, a protocol, that any network could use to communicate with any other network without requiring any changes. And that was the key. Instead of designing one perfect network, they focused on designing a protocol, a shared language that any network could adopt. And they called it Transmission Control Program, later split into TCP and IP. Eventually, they would actually articulate 4 ground rules that guided their design. The first one is that each network stands on its own. No need to rebuild anything. The new system will just layer on top of what's already there. The second one was best effort delivery. Send the data. If something's lost, the computers must fix it, not the network. There was no guarantees, no babysitting. The third rule was use simple black boxes. Routers must just pass data along. They don't track it, they don't store it. They are like traffic cops. And the last rule is no one is in charge. There was no central authority, no kill switch. Control would be spread out, making the system decentralized and resilient, even in a crisis. If you think about it, it's the same process as mailing letters the good old-fashioned way. You don't care how the post office delivers them. They can deliver it by truck, by plane, by donkey. It doesn't matter. You just want the letter to arrive. So it was December 1974, and they published a landmark paper called A Protocol for Packet Network Intercommunication. It laid out how to send datagrams or packets from one network to another. It also addressed the challenges and so on. This paper was the birth certificate of what we now call TCP/IP. In fact, it was in this document that the term Internet, which was short for Internetwork, was first used. And by 1977, they ran a legendary test. A mobile van in California sent packets over a radio network, and then a satellite link, then across the ocean to cable to London and back again. It was the first time in history that a message seamlessly jumped across 3 different networks. And it was a victory. The message actually didn't care whether it traveled by air, space, or cable. And boom, they just had invented the internet. Now, at this stage, you'd think everybody would celebrate, right? But that wasn't the case. So while Surf Khan and a bunch of their colleagues were building this open packet-switched standard, not everyone was cheering them on. In fact, a lot of powerful institutions were skeptical or outright opposed. Remember, it was the 1970s, and the world's communication infrastructure was actually dominated by telephone companies. Think AT&T in the US. In UK and France, it was the Post, Telegraph, and Telephone. These institutions had grown rich and relied on circuit switching. That was the number one technology behind the traditional telephone networks. You dial a number, the system sets up a dedicated continuous circuit between you and the other person. The line stays open for the entire call, even during silence. And the circuit switching approach did guarantee reliable, predictable connections. And at this stage, your big telecom companies invested billions of dollars to make this work at a large scale. But then you get packet switching, which was the heart of TCP/IP, and that flipped the model on its head. Because instead of reserving this fixed path, it chopped the data into smaller packets, tossed them into the network, and let them bounce through whatever routes were available. From the telecom company's perspective, that wasn't genius to them, it was chaos. They saw packet switching as unreliable, unpredictable, and unserious. And that was really evident because throughout the 1960s and 70s, the pioneers of packet switching, like Baron Davies and the rest of the people at the ARPA team, they really had trouble convincing the telecom old guard of their ideas. The AT&T engineers often sneered that packet networks could never handle real traffic as reliable as a good old-fashioned phone system. In fact, in 1972, Larry Roberts from ARPA actually approached AT&T to take over and run the ARPANET as a public network service. AT&T declined. They simply weren't interested in this oddball technology. To them, I think data networking was at best a niche market for specialized needs, not something that would challenge voice telecommunications. The Brits also dragged their feet, sticking to traditional approaches. At the time, they were also competing protocols, each with big names and powerful backers behind them. For example, in 1976, international telecom companies and government-run phone networks called PTTs introduced a system that they called X25. What was X25? Well, imagine you're sending a package. With TCP/IP, it's like dropping a bunch of smaller packages into the postal system and letting them find their own way to the destination. Some may take a weird route, but as long as they get there, it's fine. With X25, They wanted something more like FedEx overnight with tracking and signature. So every step along the way was tightly controlled, logged, and guaranteed. In technology terms, X25 used something called a virtual circuit. So even though the network was packet switched, it still tried to act like a dedicated phone line. You'd set up a connection between 2 points, and the network would guarantee that the packets flowed in that order without any loss. The pro of X25 was that it was reliable, but the con here was that it was really slow, more rigid, and less scalable. But X25 wasn't the only protocol that was popping up. Big tech companies wanted their own systems too. IBM built something called SNA, which was Systems Network Architecture in 1974. And this was designed to connect to the IBM mainframes and terminals. The Digital Equipment Corporation, DEC, also had something called DEC-Net in 1975 to connect to its own mini-computers. And the problem here is that internally they were great, but essentially they were walled gardens. They worked really well in their own ecosystems, but they didn't really play well with each other. If you were on IBM's SNA, you couldn't easily talk to a DEC-Net machine. And if you were on X25, well, you couldn't talk to anyone else on a different network. Meanwhile, TCP/IP had a totally different philosophy. TCP/IP didn't care what hardware anyone used. It didn't care who owns the network. It just wanted to be friends with everyone. And that open, flexible, permissionless approach is what gave TCP/IP the edge. Because when people wanted to connect networks, whether they were on Unix, on IBM, DEC, or even X25, TCP/IP could bridge them. It could handle that. In short, TCP/IP, yes, it was messy, but it was universal. The others were polished, but very isolated. And in the long run, openness won. And this whole conflict became known as the protocol wars. On one side, you have the TCP/IP camp, favoring open architecture, simplicity, end-to-end intelligence. On the other side, there was the telecoms and the big computer vendors. They favored centralized control, complex networks, and proprietary or bureaucratic standards. So at this stage, TCP/IP was spreading across US research networks because of its flexibility. But while that was happening, something bigger was brewing on an international stage. In 1977, the International Organization for Standardization, ISO as we know it, and the International Telegraph and Telephone Consultative Committee launched this ambitious project. They wanted to create the ultimate global unified set of protocols for all computer communications. And this was called the Open Systems Interconnection Model, or OSI. The OSI stack was designed as 7 perfectly layered protocols, from a physical connection at the bottom to application interactions at the top. It was quite complicated, but it was elegant, comprehensive, and most importantly, it was controlled by international standard bodies, governments, telecom giants, and corporates like IBM and DEC loved it. Why did they love it? Well, because OSI promised to establish some sort of formal control over networking. OSI also avoided dependence on a US military technology like TCP/IP. It was neutral and international. TCP/IP was a US military project. And lastly, OSI actually promised to create opportunities for state-run or telecom-run services to just stay in power. By the 80s, the European governments were actually mandating OSI support for public networks. And even the US National Bureau of Standards, now known as NIST or NIST, they were signaling that OSI compliance would be required for federal purchases. Unfortunately, the US Department of Defense, the very agency that funded TCP/IP, even drafted plans to transition military networks away from TCP/IP towards OSI protocols, and this was around the mid-1980s. For TCP/IP, this was a scary moment. It was no longer the experimental underdog. It was actually the unwanted pet about to be abandoned. So, it's the 1980s. A lot of people, the government, big corporate, thought that TCP/IP, It's just this weird little experiment cooked up by the US military. And because international organizations like ISO were working on something more polished and official like the OSI, that idea started to become popular because the OSI was supposedly this perfect system. It had 7 neat layers, formal protocols, blessings of the governments, telecom giants, big corporates like IBM. It had it all. On paper, the OSI was beautiful, but in practice, it wasn't forming. OSI was still stuck in meetings. Committees were still debating the standards. Companies were struggling to just make it work. It was just still in the idea phase. Meanwhile, at the same time, TCP/IP was already running. It was messy, it was unpolished, but it worked. Now, there were 2 reasons why TCP/IP took off. The first one was the grassroots adoption. In the early 80s, TCP/IP got built into BSD Unix, which was a free version of Unix from UC Berkeley. And because of this, suddenly universities across the US and even soon the world would easily hook into the growing internet. Students, professors, researchers were all now using TCP/IP. Then there was the National Science Foundation, who built the NSF-Net, and this was a backbone network to link supercomputers. And what protocol did they use? They used TCP/IP because it was working at that stage. And because of that, in 1986, the NSF-Net began connecting all the regional academic networks. And this sort of changed the internet from a military research project to a national and eventual global communication system. Even agencies like NASA or the Department of Energy, they jumped in, building their own TCP/IP-based networks as well. So it was like the snowball effect. The more people used TCP/IP, the more valuable it became. But the other good thing about TCP/IP was that it was flexible. The smart thing what TCP/IP did was that instead of fighting competition like the X25, the internet community found ways to work with it. They figured out how to carry the TCP/IP traffic over X25 networks, actually treating X25 as just another data pipeline. So this approach of, hey, we'll just ride on top of whatever's available, actually let TCP/IP sneak into places where it may have been blocked. And in contrast, OSI stuck to its formal design, making it harder to adapt or blend in. And by the early 1990s, the internet was already exploding in size. So the OSI supporters made one last push. They proposed replacing the IP part of the TCP/IP with an OSI protocol called CLNP. And this could be used to handle the network addressing. CLNP stood for Connectionless Network Protocol. It was almost like an OSI cousin to the IP. Even the internet's own governing circles, like the Internet's Architecture Board, well, they started debating whether they should use the CLNP. That's when one of the original creators of the TCP/IP, Vint Cerf, made an unforgettable statement. In 1992, at an Internet Engineering Task Force meeting, Vint Cerf walked in wearing a formal 3-piece suit, advocating for the internet's core values. He gave a really good, dignified presentation, and then he dramatically took off the suit to reveal a t-shirt underneath that said, IP over everything. And the room just erupted in laughter and cheer. It was this mic drop moment. The message was clear. The community was sticking with TCP/IP over anything. They did not want to switch to OSI. They were going to run IP everywhere, on every device, on every network. And instead of replacing IP, the internet community actually chose to improve it. Later, it turned into the IPv6 to handle growth while keeping the TCP/IP spirit. And by the mid-1990s, the protocol war was essentially over. TCP/IP had won by far. And not because it had the most committee approval, not because it was the most elegant, but because it worked. And people had already built the internet on top of it. At that stage, the World Wide Web burst into scene, also running on TCP/IP. The global takeover was just complete. So this beautiful dream of OSI was over. And the rough but ready, messy but powerful TCP/IP had ruled the day. I like the story of TCP/IP because in a way, it's a reminder that sometimes the best technology doesn't win by just being great on paper. It wins by being out there, being used, and by inspiring a community of supporters. Let's not forget the irony that the code that built the internet was almost lost, not because it failed, but because it threatened the status quo. Thanks so much for watching. If you like my content, please like, comment, and subscribe. I'll see you on the next one.